Hello, and welcome to the Sleepy Astronomer. Tonight's journey sees us scaling up to contemplate the universe's most magnificent structures as we explore the largest things in existence, from superclusters of galaxies to the cosmic web that connects everything across billions of light years. From massive galaxy clusters that dwarf our local group to the Great Wall structures that span hundreds of millions of light years, we'll journey through scales so vast they challenge human comprehension while discovering the beautiful architecture that organizes the cosmos on its grandest levels. We'll explore how these colossal structures formed, why the universe is organized in such spectacular patterns, and what the largest known objects tell us about the fundamental nature of reality itself. If you're new to these tranquil explorations of cosmic scale, welcome to our journey through the universe's most impressive architecture. And if you've drifted with me before through other astronomical wonders, it's wonderful to have you aboard for this voyage through the cosmos's grandest constructions. So, find your most comfortable position, whether you're settled in bed, relaxed on the sofa, or perhaps lying back in a chair where you can imagine the vast cosmic structures that exist far beyond our ability to directly perceive. Take a deep, peaceful breath, and let's begin our gentle journey through the universe's spectacular architecture. A voyage that will take us from galaxy clusters to cosmic walls and the web-like structure that organizes matter on the largest scales in existence. To appreciate the true giants of the universe, we need to understand how cosmic structure is organized, a hierarchy of increasingly massive objects that stretches from stars to planets to solar systems to galaxies and beyond, culminating in structures so large they span significant fractions of the observable universe itself. Let's begin our journey of scale with something familiar and work our way upward through the cosmic hierarchy. Our Earth, with a diameter of about 12,800 kilometers, seems large from our human perspective, but it's dwarfed by our Sun, which could contain over 1 million Earths within its volume. The Sun, in turn, is just one of hundreds of billions of stars in our Milky Way galaxy, which spans roughly 100,000 light-years from edge to edge. But our galaxy, magnificent as it is merely one member of what astronomers call the local group, a collection of about 80 galaxies bound together by gravity and spanning roughly 10 million light-years. The local group includes our Milky Way, the larger Andromeda Galaxy, the smaller Triangulum Galaxy, and dozens of dwarf galaxies that orbit around these larger structures, like cosmic suburbs surrounding galactic cities. Yet the local group itself is a relatively small structure in the cosmic hierarchy. It's part of the much larger Virgo supercluster, which contains thousands of galaxies spread across roughly 110 million light-years of space. The Virgo supercluster, centered on the massive Virgo cluster of galaxies, represents one of the largest gravitationally bound structures in our cosmic neighborhood. But even superclusters are not the ultimate structures in the cosmic hierarchy. In 2014, astronomers announced the discovery that our local group and the Virgo supercluster are actually part of an even more immense structure called the Laniakea supercluster, a cosmic construction that spans some 520 million light-years and contains roughly 100,000 galaxies. The name Laniakea comes from Hawaiian words meaning immense heaven, and it's a fitting description for a structure so vast that light takes over 500 million years to cross from one side to the other. If you could somehow step outside Laniakea and view it from a distance, you would see a flattened, somewhat disk-like collection of galaxies and galaxy clusters, all connected by streams of matter, that flow like cosmic rivers toward the structure's gravitational center. This hierarchical organization of cosmic structure tells a story that began shortly after the Big Bang. In the early universe, matter was distributed almost uniformly throughout space, with only tiny density fluctuations that served as seeds for future structure formation. Over billions of years, gravity amplified these small variations, causing slightly denser regions to attract more matter and grow into the cosmic web of filaments, nodes, and voids that we observe today. The process of structure formation is ongoing. Galaxies continue to merge and grow. Galaxy clusters continue to accrete new members, and the largest structures in the universe continue to evolve, though at times scales so vast that significant changes occur over hundreds of millions or billions of years. Understanding this hierarchy helps us appreciate just how extraordinary the largest cosmic structures really are. When astronomers discover a galaxy cluster containing thousands of galaxies, or a supercluster spanning hundreds of millions of light-years, they're not just finding big objects, they're uncovering the fundamental architecture that organizes matter and energy on the largest scales in the universe. The discovery of these massive structures has also revealed something surprising about the composition. The galaxies we see represent only a small fraction of the total matter in large cosmic structures. Most of the mass is in the form of dark matter, mysterious, invisible material that reveals its presence only through its gravitational effects. Galaxy clusters, for example, contain roughly 5 times more dark matter than ordinary matter. This dark matter forms a kind of invisible scaffolding that shapes the distribution of galaxies and provides the gravitational framework for the largest structures in the universe. Without dark matter, the cosmic web of filaments and voids that characterizes large-scale structure could not exist. The study of the larger structures in the universe also provides crucial insights into cosmology. Our understanding of the universe's origin, evolution, and ultimate fate. The size and distribution of galaxy clusters and superclusters provide tests of our theories about cosmic inflation, dark energy, and the fundamental parameters that govern the universe's behavior. For instance, the fact that we observe structures as large as superclusters tells us something important about the age and expansion history of the universe. If the universe were much younger, there wouldn't have been enough time for gravity to assemble such massive structures. If the universe were expanding much faster, gravity wouldn't have been able to overcome cosmic expansion to create gravitationally bound objects on such large scales. The larger structures also provide natural laboratories for studying extreme physics. Galaxy clusters contain some of the hottest gas in the universe, heated to temperatures of tens of millions of degrees by the gravitational energy released when smaller groups of galaxies merge together. This hot gas emits X-rays that can be detected by space-based telescopes, revealing the internal structure and dynamics of these cosmic giants. Some galaxy clusters also act as gravitational lenses, their immense mass warping space-time enough to bend and magnify the light from even more distant galaxies located behind them. This gravitational lensing effect allows astronomers to study galaxies that would otherwise be too faint to observe, effectively turning the larger structures in the universe into natural telescopes. The temperature and density conditions in galaxy clusters also make them cosmic laboratories for studying dark matter. When galaxy clusters collide, events that unfold over hundreds of millions of years, the dark matter, ordinary matter, and hot gas behave differently. Dark matter, which interacts only through gravity, passes through collision zones relatively unaffected. The hot gas, however, can be slowed down and heated by electromagnetic interactions during the collision. These cluster collisions have provided some of the strongest evidence for dark matter's existence. In systems like the Bullet Cluster, astronomers can map the distribution of visible matter through X-ray observations of hot gas, and total matter through gravitational lensing, separately. The fact that most of the mass is offset from the visible matter provides compelling evidence that the majority of matter in the universe is indeed dark and invisible. As we contemplate these massive structures, we begin to appreciate that we live in a universe organized on scales that dwarf human comprehension. Our entire local group of galaxies, containing hundreds of billions of stars across millions of light years, is just a tiny component of much larger structures that stretch across significant fractions of the observable universe. The cosmic web that emerges from studying the larger structures reveals a universe that is neither random nor uniform, but organized into a beautiful, complex pattern of filaments, nodes, and voids. This architecture reflects the underlying physics of gravity, dark matter, and cosmic expansion working together over billions of years to create the universe's largest objects. Perhaps most remarkably, this hierarchy of structure extends from the smallest scales to the largest. The same gravitational forces that hold planets in orbit around stars also bind galaxy clusters together and shape the cosmic web itself. The universe displays a kind of self-similarity across scales, with clustering and structure formation occurring at every level, from stellar systems to the largest superclusters. Now let's explore galaxy clusters in detail, these cosmic cities that contain thousands of galaxies and represent some of the most massive gravitationally bound objects in the universe, with masses that can exceed a quadrillion times the mass of our Sun. Imagine, if you will, a cosmic metropolis where instead of buildings and streets, we have entire galaxies, each containing hundreds of billions of stars, arranged in a three-dimensional tapestry that spans millions of light years. These are galaxy clusters, and they represent one of the most magnificent demonstrations of gravity's organizing power on truly astronomical scales. To truly appreciate what galaxy clusters represent, we need to understand how astronomers first discovered these cosmic cities. In the 1780s, Charles Messier was cataloguing fuzzy objects in the night sky that might be confused with comets. What he didn't realize was that many of these nebulae were actually entire galaxies, island universes containing billions of stars. But even more remarkably, some of the regions he observed contained multiple galaxies clustered together in the same patch of sky. It wasn't until the 1920s, when Edwin Hubble proved that these spiral nebulae were actually distant galaxies, that astronomers began to understand the true nature of what they were seeing. The Coma Cluster, one of the first galaxy clusters to be studied in detail, appeared to contain over 1,000 galaxies all moving together through space, like a vast cosmic swarm. Our own Milky Way galaxy, with its 200 to 400 billion stars, resides in what astronomers call a relatively quiet cosmic neighborhood. The local group, containing our galaxy along with Andromeda and about 80 smaller companions, is actually quite modest by cosmic standards. But scattered throughout the universe are regions where thousands of galaxies have been drawn together by gravity into dense, bustling cosmic cities that dwarf our local galactic community. The nearest major galaxy cluster to us is the Virgo cluster, located roughly 54 million light-years away in the direction of the constellation Virgo. This cosmic city contains over 2,000 galaxies spread across a region about 15 million light-years in diameter, roughly 150 times larger than our local group. At the cluster's heart sits M87, a supergiant elliptical galaxy that has become famous in recent years as the first galaxy in which astronomers successfully imaged the shadow of a supermassive black hole. M87 itself is a testament to the violent history of galaxy clusters. This cosmic giant contains several trillion stars, more than 10 times the mass of our entire Milky Way, and shows clear evidence of having grown by consuming smaller galaxies over billions of years. Its smooth, featureless appearance tells a story of countless galactic mergers that have erased the spiral arms and star-forming regions that once characterized its constituent galaxies. But Virgo, impressive as it is, represents just one example of the rich variety of cosmic architecture we find in galaxy clusters. The Coma cluster, located about 320 million light-years from Earth, contains over 1,000 large galaxies and thousands of smaller ones, all bound together in a cosmic dance that has been ongoing for billions of years. Unlike Virgo, which is still relatively nearby and shows clear individual galaxy structures, Coma is so distant that its member galaxies appear as faint smudges even in large telescopes, giving us a sense of how these cosmic cities might appear to inhabitants of distant galaxy clusters looking back at us. The Perseus cluster, another magnificent example located about 240 million light-years away, demonstrates the dynamic nature of these cosmic environments. At its center lies NGC 1275, a peculiar galaxy surrounded by delicate filaments of glowing gas that stretch for tens of thousands of light-years. These filaments, invisible to the naked eye but revealed by sensitive astronomical instruments, are actually vast streams of cool gas being drawn into the galaxy's central supermassive black hole, a process that generates enormous amounts of energy and affects the entire cluster environment. These galaxy clusters are not simply random collections of galaxies that happen to wander into the same cosmic neighborhood. They are highly organized, dynamic systems with their own internal structure and complex physics. Astronomers classify galaxy clusters based on their richness, the number of bright galaxies they contain, and their morphology, or overall shape and structure. Rich clusters like Coma and Perseus are classified as Able Richness Class 2 or 3, meaning they contain hundreds to thousands of bright galaxies within a specific radius. Poor clusters, by contrast, might contain only a few dozen bright members. The richest clusters are cosmic metropolises, while poor clusters resemble small galactic towns scattered throughout the universe. The morphological classification of clusters reveals another fascinating aspect of cosmic architecture. Some clusters, called regular or CD clusters, have smooth, spherically symmetric distributions of galaxies with a giant elliptical galaxy at the center. These represent mature, relaxed systems where smaller subgroups have merged together over billions of years to create stable, organized structures. Irregular clusters, by contrast, show clear signs of ongoing merger activity. They may have multiple centers of galaxy concentration, asymmetric shapes, or obvious substructure that reveals recent or ongoing collisions between smaller galaxy groups. These irregular clusters provide snapshots of cosmic architecture in the process of formation and evolution. At the cores of rich galaxy clusters, we typically find giant elliptical galaxies, cosmic monsters that have grown fat by cannibalizing their smaller neighbors over billions of years. These central dominant galaxies, or CD galaxies, can be 10 times more massive than our Milky Way, containing trillions of stars in smooth, featureless distributions that speak to their violent formation history. They often possess multiple nuclei, remnants of the smaller galaxies they have consumed, and extended halos of stars that can stretch for hundreds of thousands of light years. Surrounding these central giants, we find a rich ecosystem of galaxy types arranged in a clear hierarchy based on distance from the cluster center. This phenomenon, known as morphology-density relation, reveals how the cluster environment profoundly affects the evolution of its member galaxies. In the dense cluster cores, elliptical and lenticular galaxies dominate, smooth, red systems that have exhausted their star-forming gas and now contain primarily old stellar populations. These galaxies show clear signs of harassment by their neighbors, gravitational interactions that have stripped away their outer stars, triggered starbursts that quickly consumed their gas supplies, and transformed what were likely once beautiful spiral galaxies into the smooth elliptical systems we observe today. Moving outward from the cluster center, we begin to find spiral galaxies like our own Milky Way, though even these show signs of cluster membership. Many possess truncated gas disks, where the outer regions of their spiral arms have been stripped away by interactions with the hot intracluster medium. Some show distorted morphologies, with tidal tails and streams of stars pulled out by gravitational encounters with neighboring galaxies. This process of galactic transformation, sometimes called galaxy harassment, occurs through several mechanisms. High-speed encounters between galaxies, traveling at thousands of kilometers per second through the cluster, can gravitationally disturb their stellar distributions and trigger intense bursts of star formation. Ram pressure stripping occurs when galaxies plow through the hot intracluster gas at high velocities, with the gas acting like a cosmic wind that blows away the galaxy's own interstellar medium. Perhaps the most remarkable aspect of galaxy clusters, however, is what lies between the galaxies themselves. Far from being empty space, the regions between cluster galaxies are filled with an incredibly hot, thin gas known as the intracluster medium. This gas has been heated to temperatures of 10 to 100 million degrees Celsius, several times hotter than the core of the Sun, by the gravitational energy released as smaller groups of galaxies fall into the cluster and merge together. The discovery of this superheated gas revolutionized our understanding of galaxy clusters. In the 1970s, when the first X-ray satellites began observing the universe, astronomers were surprised to find that galaxy clusters were among the brightest X-ray sources in the sky. The X-ray emission comes from this hot intracluster gas, which glows brilliantly at X-ray wavelengths due to its extreme temperature. This superheated medium is invisible to optical telescopes, but space-based X-ray observatories can map the internal structure of galaxy clusters in exquisite detail. These X-ray images reveal that galaxy clusters are not static, peaceful environments, but dynamic systems where smaller subclusters are constantly merging together in slow-motion collisions that unfold over hundreds of millions of years. The intracluster medium actually contains more ordinary matter than all the galaxies in the cluster combined. In a typical galaxy cluster, the hot gas accounts for about 15% of the total mass, while the galaxies themselves contribute only about 3 to 5%. This means that most of the normal matter in galaxy clusters exists not in stars and galaxies, but in this incredibly tenuous, superheated gas that fills the space between galaxies. The remaining 80 to 85% of a cluster's mass is dark matter, mysterious, invisible material that reveals its presence only through its gravitational effects, but provides the underlying scaffolding that holds these cosmic cities together. This dark matter distribution can be mapped using a technique called gravitational lensing, where the immense mass of a galaxy cluster warps spacetime itself, bending the light from even more distant galaxies located behind the cluster. These gravitational lensing maps have revealed that dark matter in galaxy clusters forms smooth, roughly spherical halos that extend far beyond the visible galaxies. The dark matter doesn't interact electromagnetically. It doesn't shine, absorb light, or collide with itself, but its gravitational influence shapes the entire cluster structure and determines how galaxies move within the cosmic city. One of the most dramatic demonstrations of dark matter's reality comes from studying galaxy cluster collisions. When two massive galaxy clusters encounter each other, the collision unfolds like a cosmic slow-motion car crash spanning hundreds of millions of years. The dark matter in each cluster, interacting only through gravity, passes through the collision zone relatively unimpeded. But the hot intracluster gas, which can interact electromagnetically, is slowed down and heated by the collision. The most famous example of such a collision is the Bullet cluster, where two galaxy clusters collided about 150 million years ago. Gravitational lensing maps show that most of the mass in the system has separated from the hot gas visible in X-rays, providing some of the strongest evidence that the majority of matter in the universe is indeed dark and invisible. These cluster mergers are among the most energetic events in the universe since the Big Bang itself. The kinetic energy involved in a major cluster collision can exceed 10 to the 64th power joules, a number so large it's difficult to comprehend. For comparison, this is roughly equivalent to the total energy output of 1 trillion suns over their entire 10 billion year lifetimes. The process of cluster formation through mergers creates a complex thermal history in the intracluster medium. When subclusters merge, shock waves propagate through the hot gas, heating it to even higher temperatures and creating complex temperature and density structures. These shock waves can accelerate particles to enormous energies, creating some of the most powerful particle accelerators in the known universe, and generating high-energy radiation that astronomers can detect across the electromagnetic spectrum. One of the great puzzles in cluster physics is known as the cooling flow problem. Simple physics suggests that the hot gas in cluster cores should cool efficiently by radiating away its thermal energy as X-rays. As it cools, the gas should become denser and flow inward toward the cluster center, creating what astronomers call a cooling flow. However, observations show that, while some cooling occurs, the process is much less efficient than theoretical models predict. The solution to this puzzle appears to involve the supermassive black holes at the centers of dominant cluster galaxies. These cosmic monsters, containing billions of times the mass of our Sun, periodically undergo periods of intense activity, generating powerful jets of high-energy particles that heat the surrounding gas and prevent excessive cooling. This creates a delicate balance between cooling and heating that maintains the cluster atmosphere in a quasi-steady state. The study of sound waves in the intracluster medium has revealed another fascinating aspect of cluster physics. Just as sound waves can propagate through Earth's atmosphere, they can also travel through the hot, tenuous gas that fills galaxy clusters. These acoustic waves, generated by the activity of central black holes or by cluster mergers, create subtle pressure variations that astronomers can detect as temperature and density fluctuations in the X-ray emission. Perhaps most remarkably, these sound waves in galaxy clusters produce some of the deepest notes in the universe. The Perseus cluster, for example, generates sound waves with a frequency about 57 octaves below middle C, far too low for human ears to detect, but measurable by sensitive X-ray observations. These cosmic sounds provide information about the cluster's structure and the processes occurring within its hot atmosphere. The magnetic fields threading through galaxy clusters represent another frontier in cluster physics. These fields, though incredibly weak by terrestrial standards, millions of times weaker than Earth's magnetic field, extend across millions of light years and play important roles in cluster dynamics. They can confine high-energy particles, affect the propagation of shock waves, and influence how the intracluster gas flows and evolves within the cluster. Observations of radio emission from galaxy clusters reveal the presence of these magnetic fields and the high-energy particles they contain. Some clusters show enormous radio halos, diffuse emission that extends across the entire cluster and indicates the presence of high-energy electrons spiraling through cluster-wide magnetic fields. Other clusters display radio relics, elongated features that trace shock waves propagating through the intracluster medium during cluster mergers. As we contemplate the most massive galaxy clusters, we encounter structures so large they stretch the limits of what can be gravitationally bound in our universe. The most massive clusters contain the equivalent mass of a quadrillion suns. That's a 1 followed by 15 zeros. These cosmic giants formed from the merger of numerous smaller clusters over billions of years, and they represent the endpoints of hierarchical structure formation in our universe. One particularly impressive example is El Gordo, Spanish for the Fat One, a massive galaxy cluster located about 7 billion light-years from Earth. This cosmic behemoth contains the mass of 3 quadrillion suns and spans several million light-years across. What makes El Gordo particularly interesting is that it formed when the universe was only about half its current age, suggesting that massive structure formation occurred earlier and more rapidly than many models predicted. The Able 2029 cluster represents another extreme example of cosmic architecture. Located about 1 billion light-years away, this cluster contains thousands of galaxies arranged around one of the largest known galaxies in the universe, a supergiant elliptical galaxy that contains more than 1 trillion stars and measures over 5 million light-years across. This central galaxy alone is larger than the distance between our Milky Way and the Andromeda Galaxy. Despite their violent formation history, galaxy clusters represent islands of relative stability in an expanding universe. While the universe as a whole continues to expand, carrying distant galaxies ever farther from us, the galaxies within a cluster are gravitationally bound and will remain together indefinitely. In fact, as the universe ages and expansion accelerates due to dark energy, galaxy clusters will become increasingly isolated island universes, eventually losing all contact with the rest of the cosmos. This future evolution of galaxy clusters provides a sobering perspective on cosmic timescales. As dark energy continues to accelerate the universe's expansion, the space between galaxy clusters will grow at an ever-increasing rate. Eventually, inhabitants of galaxies within our local group, assuming it eventually merges with a Virgo cluster, will see a night sky containing only their local cluster galaxies. The rest of the universe will have expanded beyond the cosmic horizon, becoming forever invisible and unreachable. But even within these future island universes, evolution will continue. Galaxy interactions within clusters will persist, gradually transforming the population from a mix of spirals and ellipticals to a predominantly elliptical population. The central dominant galaxies will continue to grow by consuming their neighbors, eventually creating single enormous galaxies containing most of the cluster's stellar mass. The study of galaxy clusters has also provided crucial insights into the universe's composition and evolution. The abundance of galaxy clusters at different cosmic epochs, how many exist now compared to the early universe, provides a sensitive test of cosmological models. The fact that we observe fewer massive clusters in the early universe than we do today confirms that structure formation is an ongoing process, with the largest objects forming relatively recently in cosmic history. This cluster abundance evolution has become one of the most powerful tools for constraining the properties of dark energy. Because massive clusters are so rare and difficult to form, their numbers are extremely sensitive to the expansion history of the universe. By carefully counting clusters at different distances, and therefore at different cosmic epochs, astronomers can trace how dark energy has affected structure formation over billions of years. Modern surveys like the Dark Energy Survey, the South Pole Telescope, and the upcoming Euclid space mission are using galaxy clusters as cosmic laboratories to probe the nature of dark energy and test our understanding of fundamental physics. These observations are revealing that the universe's composition is even more exotic than previously thought, with dark energy making up about 68% of the total energy density, dark matter contributing 27%, and ordinary matter, everything we can see, accounting for only 5%. The temperature structure within galaxy clusters also tells fascinating stories about their formation and evolution. The hottest gas is typically found in the cores of clusters, where the gravitational potential is deepest and where the most violent merger activity has occurred. Moving outward from the cluster center, the gas temperature generally decreases, creating complex temperature maps that reflect each cluster's unique merger history. Some clusters show clear evidence of recent major mergers in their temperature maps. The Coma cluster, for example, displays temperature substructure that reveals the ongoing merger of two massive subclusters. Other clusters, like Perseus, show more relaxed temperature profiles, characteristic of systems that haven't experienced major disruptions for several billion years. Perhaps most remarkably, galaxy clusters continue to grow and evolve even today. Observations show that massive clusters are still accreting smaller groups of galaxies from their surroundings, adding new members to their cosmic cities at a rate of several new galaxies every billion years. This ongoing accretion process generates shock waves and turbulence in the intracluster medium, creating a dynamic, ever-changing environment that continues to shape the properties of cluster galaxies. The sheer scale of these cosmic cities can be difficult to internalize. If you could somehow travel at the speed of light, the fastest possible speed in the universe, it would still take you millions of years to cross from one side of a large galaxy cluster to the other. During that journey, you would pass by thousands of galaxies, each containing hundreds of billions of stars, all held together in a gravitational embrace that has persisted for billions of years. As we prepare to venture beyond individual clusters to explore the even larger structures that connect them, take a moment to appreciate these cosmic cities in which we find ourselves. Our local group may be heading toward an eventual merger with the Virgo cluster, meaning that in several billion years, our descendants might find themselves living in one of these bustling cosmic metropolises, surrounded by thousands of neighboring galaxies in a gravitational community that spans millions of light years. Galaxy clusters remind us that the universe is not a lonely place, but rather a cosmos where matter naturally organizes itself into communities, cosmic cities, where thousands of galaxies live together in gravitational harmony, connected by hot gas and invisible dark matter, shaped by magnetic fields and sound waves, all part of an architectural hierarchy that extends to the largest scales imaginable. These magnificent structures represent gravity's greatest achievements, cosmic monuments to the organizing power of the fundamental forces that shape our universe on its grandest scales. Beyond individual clusters lies an even grander structure, the cosmic web itself, a vast network of filaments and voids that organizes matter on the largest scales and reveals the universe's fundamental architecture, a delicate ethereal framework that connects all cosmic structures across billions of light-years of space. If galaxy clusters are the cosmic cities we explored in our last chapter, then the cosmic web is the vast network of highways, rivers, and open countryside that connects these metropolitan areas. It is perhaps the most beautiful and mysterious aspect of cosmic architecture, an intricate lattice of matter and energy that spans the entire observable universe and reveals the fundamental patterns underlying all cosmic structure. To understand the cosmic web, we must first step back and consider one of the most surprising discoveries in the history of astronomy. When astronomers first began mapping the positions of galaxies in three-dimensional space during the 1970s and 1980s, they expected to find a relatively uniform distribution of matter. Galaxies scattered more or less randomly throughout space, perhaps with some tendency to cluster together, but without any large-scale pattern or organization. What they discovered instead was so unexpected and beautiful that it revolutionized our understanding of cosmic architecture. Galaxies are not randomly distributed through space, but are organized into an intricate network of filaments, sheets, and nodes, separated by vast regions that are almost entirely empty. This cosmic web extends as far as we can observe, suggesting that it may be a fundamental property of the universe itself. The story of this discovery begins in the late 1970s with astronomers at the Harvard-Smithsonian Center for Astrophysics, who were conducting what seemed like routine observations. Margaret Geller, John Huchra, and their colleagues were measuring the distances to thousands of galaxies to create the first comprehensive three-dimensional map of our cosmic neighborhood. They expected this map to show galaxies distributed fairly uniformly through space, with perhaps some clustering around the Virgo cluster and other known galaxy groups. Instead, when they plotted their first results in 1989, they discovered something extraordinary. The galaxies in their survey were arranged in a pattern that looked remarkably like a cross-section through a sponge or soap foam. Galaxies were concentrated along thin filaments and broad sheets, surrounding enormous bubble-like regions that appeared almost completely empty of matter. The most striking feature in their map was a vast structure they named the Great Wall, a sheet of galaxies stretching across at least 500 million light-years of space. This was not a wall in the conventional sense, but rather a concentration of thousands of galaxies arranged in a thin, elongated structure that seemed to separate two enormous regions of space containing almost no galaxies at all. The Great Wall was unlike anything astronomers had expected to find in the universe. Here was a structure so large that light took 500 million years to travel from one end to the other, yet it was also surprisingly thin, only about 15 million light-years thick in most places. It was as if the cosmos had organized itself into a vast architectural framework, with matter concentrated along the surfaces of enormous cosmic bubbles. As more comprehensive surveys followed, this pattern became even more dramatic and widespread. The 2-degree field galaxy redshift survey, completed in the early 2000s, mapped the positions of over 200,000 galaxies and revealed that the honeycomb-like pattern observed in the original CFA survey extended as far as telescopes could see. Everywhere astronomers looked, they found the same basic architecture: filaments of galaxies surrounding vast empty regions called cosmic voids. The Sloan Digital Sky Survey, which has mapped over 1 million galaxies across more than a quarter of the sky, revealed the cosmic web in unprecedented detail. When viewed in 3 dimensions, the universe resembles a vast cosmic sponge, with galaxies concentrated along thin filaments and broad sheets that define the edges of enormous empty bubbles. These structures exist on every scale that astronomers can observe, from small filaments connecting nearby galaxy groups to vast walls stretching across billions of light years. The cosmic filaments themselves are the highways of the universe, channels along which matter has flowed and concentrated over billions of years of cosmic evolution. They typically stretch for hundreds of millions of light years, containing chains of galaxies and galaxy clusters connected by streams of gas and invisible dark matter. Some filaments are remarkably straight, like cosmic superhighways connecting distant galaxy clusters, while others show complex branching patterns that create intricate networks of smaller connecting roads. At the intersections where multiple filaments meet, we find the nodes of the cosmic web, the densest regions where the most massive galaxy clusters have formed over cosmic time. These nodes represent the cosmic equivalent of major metropolitan areas, where the universe's matter has concentrated most efficiently under the influence of gravity. The Coma cluster, Perseus cluster, and other massive galaxy clusters we explored in our previous chapter all sit at such nodes, positioned at the intersections of major cosmic filaments. Between these filaments lie the cosmic voids, vast regions of space that contain remarkably few galaxies and appear to be largely empty. These voids are not completely devoid of matter, but their densities are so low that they contain less than 10% of the average matter density of the universe. To appreciate their emptiness, consider that if you were to take all the matter in a typical cosmic void and spread it uniformly throughout the same volume, it would be more tenuous than the best vacuum ever created in a terrestrial laboratory. The Boötes void, also known as the Great Nothing, represents one of the most spectacular examples of these cosmic empty regions. Discovered in 1981 by astronomers studying the distribution of galaxies in the direction of the constellation Boötes, this enormous bubble of space spans roughly 330 million light-years in diameter. Within this vast volume, large enough to contain thousands of galaxies like our Milky Way, astronomers have found fewer than 60 known galaxies. To truly grasp the emptiness of the Boötes void, imagine that our local group of galaxies were placed at its centre. The nearest neighbouring galaxy would be over 150 million light-years away, nearly 60 times more distant than our nearest major neighbour, the Andromeda Galaxy. An observer in such a location would see a night sky almost devoid of external galaxies, creating a profound sense of cosmic isolation that would have dramatically altered humanity's understanding of the universe. Our entire local supercluster, containing thousands of galaxies spread across 100 million light-years of space, could fit comfortably within the Boötes void with room to spare. The void is so large that if it were filled with galaxies at the average density found elsewhere in the universe, it would contain more than 2,000 bright galaxies instead of the few dozen that actually exist there. Other notable cosmic voids demonstrate the variety and scale of these empty regions. The Capricornus void spans about 230 million light-years, while the Sculptor void stretches across 150 million light-years. The local void, much smaller at about 45 million light-years across, lies relatively close to our own galaxy and helps explain why our cosmic neighbourhood appears less densely populated than average regions of the universe. These cosmic voids are not perfectly spherical bubbles, but show complex, interconnected shapes that reflect the underlying physics of structure formation. They tend to be elongated and connected to other voids through narrow channels, creating a network of empty space that mirrors the filamentary network of matter concentration. Some voids show internal structure, with smaller subvoids nested within larger ones, creating a hierarchy of emptiness that extends across multiple scales. The few galaxies that do exist within cosmic voids often display unusual properties that provide clues about how environment affects galactic evolution. Void galaxies tend to be smaller, bluer, and more actively forming stars than galaxies found in denser environments. They appear to have evolved in relative isolation, largely undisturbed by the gravitational interactions and galaxy mergers that shape galactic evolution in denser regions. The formation of the cosmic web traces back to the earliest moments of cosmic history, when the universe was less than 400,000 years old and still filled with hot, dense plasma. At that time, the universe was remarkably smooth and uniform, but not perfectly so. Tiny quantum fluctuations during the universe's earliest moments had created regions of slightly higher and lower density. Variations so small they amounted to only 1 part in 100,000. These primordial density fluctuations, first detected as temperature variations in the cosmic microwave background radiation, served as the seeds from which all cosmic structure would eventually grow. When the universe finally cooled enough for atoms to form and the cosmic microwave background was released, these tiny variations became frozen into the distribution of matter throughout space. Over millions and billions of years, the process of gravitational instability caused these initially tiny fluctuations to grow into the cosmic web we observe today. Regions that were slightly denser than average began to attract more matter through gravitational attraction, growing slowly but steadily over cosmic time. Meanwhile, regions that were slightly less dense became relatively emptier as matter flowed away from them toward the gravitationally attractive dense regions. This process created a kind of cosmic avalanche effect, where small initial differences became amplified over billions of years, into the dramatic contrast we see today between dense filaments and nearly empty voids. The densest regions in the primordial fluctuation pattern became the sites where galaxy clusters would eventually form, while the least dense regions evolved into the vast cosmic voids that separate the filamentary network. The remarkable thing about this process is that it preserves information about the early universe across billions of years of cosmic evolution. The pattern of filaments and voids that we observe today directly reflects the quantum fluctuations that existed when the universe was less than a second old. In a very real sense, the cosmic web is a fossil record of the universe's birth, stretched across the entire observable cosmos, and written in the distribution of galaxies and matter. The cosmic web reveals itself most clearly when astronomers create what are called redshift surveys, three-dimensional maps showing not just where galaxies appear in the sky, but how far away they are. These surveys require measuring the redshift of thousands or millions of galaxies, a painstaking process that has only become feasible with modern automated telescopes and efficient spectrographs. When these three-dimensional maps are displayed, the cosmic web appears with stunning clarity. Galaxies trace out thin filaments that stretch across hundreds of millions of light years, connect at nodes where galaxy clusters reside, and surround vast empty regions that contain almost no visible matter. The pattern is so striking and universal that it appears wherever astronomers have sufficient data to map cosmic structure in detail. Different types of cosmic structures reveal different aspects of the cosmic web architecture. Bright elliptical galaxies, which tend to be found in dense environments, clearly outline the nodes and major filaments where matter has concentrated most effectively. Spiral galaxies like our Milky Way are more commonly found along the thinner filaments and in the outer regions of galaxy clusters, where the environment is less extreme and gas can still support active star formation. Dwarf galaxies, the most numerous type of galaxy in the universe, provide another perspective on cosmic web structure. These small, faint galaxies are found throughout the cosmic web, but show a preference for certain environments. While they can survive in the dense cores of galaxy clusters, they are most abundant in the outer regions of clusters and along the connecting filaments, where gravitational tidal forces are less likely to disrupt their fragile structure. The cosmic web also reveals itself through the distribution of different galaxy types and properties. Galaxies in dense filaments and cluster cores tend to be older, redder, and less actively forming stars, suggesting that the cosmic web environment has a profound influence on how galaxies evolve over cosmic time. Galaxies and cosmic voids, by contrast, often appear younger and more actively star-forming, as if they had been allowed to evolve in relative peace, without the disruptive influences of gravitational interactions with neighbours. As we contemplate this magnificent architectural framework that organises the entire observable universe, we begin to appreciate that the cosmic web represents something far more profound than just the largest structures in existence. It is the fundamental organising principle that connects everything from individual galaxies to the largest superclusters, creating a universe that is neither uniform nor random, but beautifully and intricately structured on the grandest scales imaginable. The discovery of the cosmic web has transformed our understanding of cosmic evolution and our place within the universe. We now know that our Milky Way galaxy sits within this vast network, connected through streams of matter and energy to structures billions of light years away. The cosmic web provides the framework within which all cosmic evolution occurs, the stage upon which the drama of galaxy formation and evolution plays out across billions of years of cosmic time. As we prepare to explore how this cosmic web is shaped by invisible forces and hidden matter, we carry with us this image of a universe organized into a pattern of extraordinary beauty and complexity, a cosmic architecture that reveals the underlying unity and interconnectedness of all structures in the cosmos, from the smallest dwarf galaxies to the largest walls of matter that span billions of light years of space. The magnificent cosmic web we explored in our previous chapter, that intricate network of filaments and voids stretching across billions of light years, represents only the visible tip of an even grander architectural framework. Beneath the distribution of galaxies and glowing gas lies an invisible scaffolding of dark matter that provides the gravitational foundation for all cosmic structure, shaping the universe's architecture in ways both profound and mysterious. To understand how the cosmic web truly formed and continues to evolve, we must venture into the realm of the invisible, a universe dominated by mysterious dark matter that reveals its presence only through its gravitational influence on the cosmos around it. This dark matter makes up roughly 85% of all matter in the universe, yet it interacts with light so weakly that we cannot see it directly with any telescope ever built. The story of dark matter's role in cosmic architecture begins with computer simulations that have revolutionized our understanding of structure formation. Starting in the 1970s and 1980s, astronomers began using powerful computers to model how the universe might have evolved from the smooth, nearly uniform conditions observed in the cosmic microwave background to the complex web-like structure we see today. These simulations begin with the tiny density fluctuations that existed when the universe was only 400,000 years old, variations of just one part in 100,000 that served as the seeds of all future structure. The simulations then follow billions of particles representing dark matter as they evolve under the influence of gravity and the universe's expansion over billions of years of cosmic time. The results of these simulations are nothing short of remarkable. Without including any information about where galaxies actually are located, the simulations naturally produce a cosmic web that looks strikingly similar to the real universe. Filaments of dark matter particles naturally form long, thin streams, connecting massive nodes where dark matter concentrates into dense halos. Between these filaments lie vast voids, where dark matter densities drop far below the cosmic average. When astronomers overlay the positions of real galaxies onto these dark matter simulations, they find an almost perfect match. Galaxies preferentially form within the densest dark matter halos, particularly at the nodes where multiple filaments intersect. This correspondence strongly suggests that dark matter provides the underlying framework that determines where galaxies can form and how they are distributed throughout the universe. The Millennium simulation, completed in 2005, represented a watershed moment in our understanding of cosmic structure formation. This massive computational effort followed the evolution of over 10 billion dark matter particles through a cubic region of space 2 billion light-years on each side. The simulation required months of computing time on some of the world's most powerful supercomputers, but the results provided unprecedented insight into how dark matter shapes cosmic architecture. The simulation revealed that dark matter naturally organizes itself into a hierarchy of structure, with smaller clumps merging together over cosmic time to form progressively larger halos. The largest of these halos, containing masses equivalent to hundreds of trillions of suns, mark the locations where the most massive galaxy clusters form. Smaller halos, with masses similar to individual galaxies, are scattered throughout the cosmic web, but show a clear preference for the dense filamentary regions. More recent simulations, such as the Illustrious and Eagle projects, have added the physics of ordinary matter to these dark matter frameworks, showing how gas flows along the dark matter filaments and eventually cools and condenses to form stars within galaxies. These simulations reveal that the cosmic web is not just a network of dark matter, but a dynamic system where ordinary matter flows like cosmic rivers along the dark matter highways. This ordinary matter, primarily hydrogen and helium gas, plays a crucial role in connecting the visible and invisible components of cosmic structure. As gas flows along dark matter filaments, it becomes heated by shock waves and gravitational compression to temperatures of millions of degrees, creating what astronomers call the warm-hot intergalactic medium. This superheated gas is too hot to emit visible light, but not quite hot enough to be a strong X-ray source, making it extremely difficult to detect directly. The warm-hot intergalactic medium represents a major component of the cosmic web that remained largely hidden until recent technological advances allowed astronomers to detect its faint signals. Using ultraviolet and X-ray telescopes, researchers have begun to map this hot gas as it flows through the cosmic web, revealing that the space between galaxies is far from empty, but filled with tenuous streams of million-degree gas. This discovery has helped solve one of astronomy's great mysteries, the missing baryon problem. Observations of the cosmic microwave background radiation tell us precisely how much ordinary matter should exist in the universe. But when astronomers counted up all the stars, planets, gas clouds, and other visible matter they could find, they came up short by about half. The missing ordinary matter appears to reside in this warm, hot, intergalactic medium that permeates the cosmic web. Recent observations using the Hubble Space Telescope and other instruments have detected absorption lines from highly ionized oxygen and other elements in the spectra of distant quasars, providing direct evidence for this hot intergalactic gas. The gas appears to be distributed along the cosmic web filaments predicted by computer simulations, confirming that the space between galaxies contains vast reservoirs of hot, diffuse matter that had previously escaped detection. The relationship between dark matter and ordinary matter in the cosmic web creates a complex feedback system that profoundly influences how galaxies form and evolve. Dark matter provides the gravitational wells where ordinary matter can collect and cool, but the process of star formation and stellar feedback can drive gas out of galaxies and back into the intergalactic medium. This creates a cosmic recycling system where matter flows back and forth between galaxies and the cosmic web over billions of years. Environmental effects within the cosmic web play a crucial role in determining the properties and evolution of galaxies. Galaxies located in dense filaments experience frequent gravitational interactions with their neighbors, leading to enhanced rates of galaxy mergers and the transformation of spiral galaxies into elliptical systems. The hot gas that fills these dense regions can strip away the cold gas reservoirs that fuel star formation, gradually shutting down stellar birth in cluster galaxies. By contrast, galaxies in cosmic voids evolve in relative isolation, largely undisturbed by the environmental effects that shape galactic evolution in denser regions. Void galaxies tend to retain their cold gas supplies longer, maintaining active star formation and preserving the blue colors and spiral structures characteristic of younger galactic populations. This environmental dependence means that a galaxy's location within the cosmic web largely determines its evolutionary fate. The cosmic web also influences galaxy formation through the process of cold accretion, where streams of cool gas flow along dark matter filaments directly into galactic halos. Computer simulations show that this cold accretion is most efficient in lower mass halos and at high redshifts, when the universe was younger and denser. As cosmic time progresses and dark energy begins to dominate the universe's expansion, these cold streams become increasingly disrupted by the heating effects of structure formation. The future evolution of the cosmic web is intimately connected to the mysterious dark energy that is causing the universe's expansion to accelerate. As dark energy continues to drive space itself to expand at ever-increasing rates, the cosmic web will gradually become stretched and diluted. The larger structures will become increasingly isolated as the space between them grows faster than light can travel. Computer simulations of the cosmic web's future evolution paint a picture of increasing cosmic isolation. Over the next 100 billion years, galaxy clusters will merge with their neighbors to form larger, gravitationally bound systems, but these merged clusters will become increasingly isolated from the rest of the universe. Eventually, each cluster will become a cosmic island universe, surrounded by an ever-expanding void that grows faster than any signal can cross. Within these future island universes, the cosmic web structure will persist on smaller scales. Dark matter filaments will continue to channel matter flow within galaxy clusters, and the processes of galaxy formation and evolution will continue, albeit at a reduced rate, as the supply of fresh gas from the intergalactic medium becomes exhausted. The warm, hot intergalactic medium will cool and rarefy as cosmic expansion stretches it to lower and lower densities. The study of dark matter's role in cosmic web formation has also revealed profound connections between the largest and smallest scales in the universe. The same dark matter, halos that host individual galaxies, show internal structure that mirrors the cosmic web, with subhalos and streams of dark matter that reflects the hierarchical nature of structure formation. Even within our own Milky Way, astronomers have detected streams and substructures in the dark matter halo that preserve information about ancient merger events. Recent advances in gravitational lensing techniques have allowed astronomers to map the distribution of dark matter in cosmic web filaments with unprecedented precision. By measuring how the gravity of cosmic web structures bends the light from background galaxies, researchers can create detailed maps of where the dark matter is located, independent of where the visible galaxies happen to be. This dark matter maps reveal that the cosmic web extends far beyond the distribution of luminous galaxies. Dark matter filaments stretch continuously between galaxy clusters, often containing more mass than the clusters themselves. The filaments show complex internal structure, with dense cores surrounded by more diffuse halos, and exhibit branching patterns that create networks within networks on multiple scales. The magnetic fields that thread through cosmic web filaments represent another invisible component of large-scale structure. These fields, though incredibly weak by terrestrial standards, are amplified and organized by the flow of gas along dark matter filaments. Computer simulations suggest that these cosmic magnetic fields may play important roles in regulating star formation and influencing the evolution of galaxies within the cosmic web. Observations of radio emission from cosmic web filaments provide indirect evidence for these magnetic fields and the high-energy particles they accelerate. Some filaments connecting galaxy clusters show faint radio emission that traces the underlying dark matter structure, revealing magnetic fields that extend across tens of millions of light-years and participate in the cosmic web's evolution over billions of years. The cosmic web's dark matter architecture also provides natural laboratories for testing fundamental physics under extreme conditions. The vast scales involved, hundreds of millions of light-years, allow astronomers to test whether the laws of gravity remain constant across enormous distances and cosmic times. The delicate balance between matter, dark matter, and dark energy that governs cosmic web formation provides exquisitely sensitive tests of our understanding of fundamental forces. As we contemplate this invisible architecture that underlies all cosmic structure, we begin to appreciate that the universe we observe is merely the visible surface of a far grander and more complex reality. The galaxies that light up the cosmic web are like cities built along the intersections of vast, invisible highways, constructed from dark matter and threaded with streams of million-degree gas. The cosmic web reminds us that the universe operates on principles far beyond our everyday experience, where invisible matter dominates visible matter by a factor of 5 to 1, where empty space is filled with superheated gas, and where the fundamental architecture of reality is shaped by forces and substances that reveal themselves only through their gravitational influence on the cosmos around them. This invisible scaffolding connects every structure in the universe, from the smallest dwarf galaxies to the largest superclusters, creating a cosmic architecture so vast and complex that we are only beginning to understand its full implications. As we prepare to explore the record-holding structures within this framework, we carry with us this image of a universe built upon invisible foundations, shaped by dark forces, and connected through networks of matter and energy that span the entire observable cosmos and beyond. Within the magnificent cosmic web we have been exploring lie structures so vast that they challenge our very understanding of what is possible in our universe, cosmic constructions that stretch across billions of light years and represent the ultimate expression of matter's ability to organize itself into coherent patterns on the grandest scales imaginable. These are the universe's record holders, the largest known structures in existence, and they push the boundaries of what cosmological theory suggests should be possible. To appreciate their true magnitude, We must venture beyond even the impressive galaxy clusters and cosmic filaments we have encountered so far, into a realm where individual structures can span significant fractions of the observable universe itself. The current holder of the title, largest structure in the universe, is a cosmic construction with a fittingly grand name, the Hercules-Corona Borealis Great Wall. Discovered in 2013 through careful analysis of gamma-ray burst data, this structure represents something so large that it challenges fundamental assumptions about how uniform the universe should appear on the larger scales. Stretching across roughly 10 billion light-years of space, approximately 10% of the diameter of the observable universe, the Hercules-Corona Borealis Great Wall is a loose association of galaxy clusters, superclusters, and cosmic filaments that appears to form a coherent structure, spanning from the constellation Hercules to Corona Borealis. To put this scale in perspective, light from one end of this structure takes 10 billion years to reach the other end, meaning that if you could somehow observe both ends simultaneously, you would be seeing them as they existed at different epochs in cosmic history. The discovery of this cosmic giant came not from traditional galaxy surveys, but from studying gamma-ray bursts, the most powerful explosions in the universe that occur when massive stars collapse into black holes or when neutron stars collide. Astronomers noticed that these gamma-ray bursts showed a peculiar clustering pattern in the direction of Hercules and Corona Borealis, suggesting the presence of an enormous concentration of matter that was influencing the distribution of galaxies and star formation across a vast region of space. What makes the Hercules-Corona Borealis Great Wall so remarkable is not just its size, but what its existence implies about the nature of cosmic structure formation. According to the cosmological principle, one of the fundamental assumptions of modern cosmology, the universe should appear homogeneous and isotropic when viewed on sufficiently large scales. In other words, there should be a scale beyond which the universe looks essentially the same in all directions, with no structures larger than a certain size. Most estimates suggest that this scale of homogeneity should be reached at distances of about 1.2 billion light-years. Structures much larger than this should not exist, because there hasn't been enough time since the Big Bang for gravity to organize matter into coherent patterns on such vast scales. Yet the Hercules-Corona Borealis Great Wall is nearly 10 times larger than this theoretical limit, raising profound questions about our understanding of cosmic evolution and structure formation. The existence of such massive structures also challenges our understanding of the early universe and the processes that created the initial density fluctuations from which all cosmic structure grew. If the primordial fluctuations that seeded structure formation were truly random, as most theories suggest, then structures as large as the Hercules-Corona Borealis Great Wall should be extraordinarily rare, perhaps so rare that we would not expect to find even one in the observable universe. Before the discovery of the Hercules-Corona Borealis Great Wall, the title of largest known structure belonged to the Sloan Great Wall, a slightly smaller but still magnificent construction discovered in 2003 during the Sloan Digital Sky Survey. This cosmic architecture spans approximately 1.37 billion light-years and contains thousands of galaxies arranged in a complex pattern of filaments and sheets. The Sloan Great Wall demonstrates the hierarchical nature of cosmic structure in beautiful detail. When viewed at low resolution, it appears as a simple wall-like concentration of galaxies. But as astronomers examine it more closely, they discover that it contains multiple levels of organization, smaller walls and filaments nested within the larger structure, creating a fractal-like pattern that reveals complexity on every scale that can be observed. What makes the Sloan Great Wall particularly interesting is its detailed structure and the wealth of observational data available about its constituent galaxies. Unlike more distant structures that appear as faint statistical enhancements in galaxy counts, the Sloan Great Wall is close enough that astronomers can study individual galaxies within it, examining how their properties are influenced by their location within this vast cosmic construction. Galaxies within the Sloan Great Wall show clear signs of environmental effects related to their position within the larger structure. Those located in the densest regions tend to be older, redder elliptical galaxies that have exhausted their gas supplies and ceased forming new stars. Galaxies in the outer regions of the wall retain more of their original spiral structure and continue active star formation, suggesting that the wall's environment influences galactic evolution in complex ways. The wall also shows evidence of ongoing dynamics, with streams of galaxies flowing along its filamentary structure and smaller galaxy groups merging into larger clusters within its framework. This suggests that even these larger structures continue to evolve and grow, accreting matter from their surroundings over billions of years of cosmic time. Another remarkable example of cosmic scale architecture is the CFA2 Great Wall, also known simply as the Great Wall, which was the first such structure to be discovered and mapped in detail. Spanning at least 500 million light-years, this wall of galaxies was revealed in the late 1980s by the Harvard-Smithsonian Center for Astrophysics Redshift Survey, and represents a foundational discovery that changed our understanding of large-scale structure. The CFA2 Great Wall appears as a thin sheet of galaxies separating two enormous cosmic voids, creating a soap bubble-like structure that extends far beyond the original survey boundaries. What makes this wall particularly significant is not just its size, but its role in revealing the cosmic web architecture that we now know characterizes the entire universe. When astronomers first plotted the three-dimensional positions of galaxies in this region, they discovered that galaxies were not randomly distributed, but were concentrated along the surfaces of vast bubble-like regions. This discovery fundamentally changed how we think about cosmic structure, revealing that the universe is organized more like a cosmic foam or sponge than like a random distribution of matter. The Pisces Cetus supercluster complex represents another example of large-scale organization, though it differs from walls like Sloan and CFA2 in that it appears more as a loose association of galaxy clusters and superclusters rather than a thin wall-like structure. Spanning roughly 1 billion light-years, this complex includes our own local supercluster, as well as the Perseus-Pisces supercluster, and several other massive concentrations of galaxies. What makes the Pisces-Cetus supercluster complex particularly interesting is that it appears to be a genuine gravitationally bound structure, meaning that its components are not simply moving apart with the expansion of the universe, but are actually held together by their mutual gravitational attraction. This makes it one of the largest gravitationally coherent structures known, representing a scale where cosmic expansion and gravitational attraction are nearly balanced. The Boss Great Wall, discovered more recently through the Baryon Oscillation Spectroscopic Survey, represents another magnificent example of large-scale structure. Spanning approximately 1 billion light-years, this structure was identified through sophisticated statistical analysis of galaxy clustering patterns across enormous volumes of space. What makes the Boss Great Wall particularly noteworthy is the precision with which it has been mapped and characterized. Modern surveys like BOSS can measure the distances to millions of galaxies with unprecedented accuracy, allowing astronomers to trace large-scale structure in 3 dimensions with remarkable detail. The Boss Great Wall appears as a complex network of filaments and nodes, revealing the cosmic web's architecture on scales approaching the largest structures in the universe. These massive walls and complexes raise fundamental questions about the nature of structure formation and the limits of cosmic architecture. If such large structures can form and persist over billions of years, what does this tell us about the initial conditions of the universe and the processes that shaped its evolution? One possibility is that the primordial density fluctuations from which all structure grew were not entirely random, but contained correlations or patterns on very large scales that we do not yet fully understand. Another possibility is that our understanding of structure formation itself is incomplete, and that there are physical processes operating on cosmic scales that can organize matter more efficiently than current theories predict. The existence of these vast structures also has implications for our understanding of cosmic inflation, the hypothetical period of rapid expansion that may have occurred during the universe's first moments. Different models of inflation predict different patterns of primordial fluctuations, and the observed properties of the larger structures provide tests of these models. Some researchers have suggested that the larger structures we observe may not be coherent objects at all, but rather statistical fluctuations in the cosmic web that happen to create the appearance of organization on vast scales. According to this view, structures like the Hercules-Corona Borealis Great Wall may be more like cosmic mirages, patterns that emerge from the random distribution of matter but do not represent genuine physical structures. However, the growing catalogue of very large structures suggests that such statistical explanations may be insufficient. The Hercules-Corona Borealis Great Wall, the Sloan Great Wall, the CFA2 Great Wall, and other massive structures appear to be too numerous and too large to be explained as random fluctuations in an otherwise uniform universe. The study of these largest structures also provides insights into the geometry and topology of the universe itself. If the universe has complex topology, if space is curved or connected in ways that are not immediately apparent, then some apparent large-scale structures might actually be optical illusions, created by light traveling around closed paths through curved space-time. Current observations suggest that the universe is very nearly flat on large scales, which would rule out most exotic topologies. However, the possibility remains that subtle topological effects could influence our perception of the larger structures, and ongoing surveys are designed to test for such effects. As we contemplate these record-holding structures, we must also consider their ultimate fate as the universe continues to evolve under the influence of dark energy. The accelerating expansion of space means that the largest structures we observe today may represent a kind of cosmic high-water mark, the most extensive organizations of matter that will ever exist. As dark energy continues to dominate cosmic evolution, it will become increasingly difficult for gravity to maintain coherence across such vast distances. The largest structures may gradually lose their cohesion as space itself expands faster than gravitational forces can hold them together. This suggests that we may be living during a special epoch in cosmic history when the universe's largest architectural achievements are visible and accessible to observation. The walls and complexes we observe today preserve information about cosmic conditions billions of years ago, when the universe was denser and structure formation proceeded more rapidly. They serve as fossil records of cosmic evolution, encoding information about the initial conditions of the universe, the nature of dark matter and dark energy, and the fundamental processes that shape cosmic architecture on the grandest scales. As we prepare to explore other cosmic extremes and mysteries, we carry with us this sense of the universe as a place capable of creating structures so vast that they approach the limits of what is theoretically possible. These cosmic giants remind us that we live in a universe of extraordinary architectural ambition, where matter organizes itself into patterns of such magnificence and scale that they challenge our deepest understanding of physical law and cosmic evolution. While the great walls and filaments we explored in our previous chapter represent the universe's largest connected structures, scattered throughout the cosmic web are individual objects and phenomena that push the boundaries of cosmic extremes in their own remarkable ways, mysterious concentrations of matter and energy that challenge our understanding of how the universe builds its most spectacular monuments. These cosmic record holders represent the universe at its most ambitious and puzzling, from collections of the most luminous objects in existence to individual galaxies that dwarf our entire local group, and mysterious regions where the fabric of space-time itself seems strangely empty and cold. Each of these extremes tells a unique story about the processes that shape cosmic evolution on its grandest scales. Perhaps no cosmic structure has generated more controversy and scientific debate than the huge large quasar group, known to astronomers simply as the huge LQG. Discovered in 2012, this enormous collection of 73 quasars spans approximately 4 billion light-years across, a scale so vast that it appears to violate fundamental principles about how uniform the universe should be on large scales. Quasars themselves are among the most extraordinary objects in the universe, supermassive black holes surrounded by brilliantly glowing disks of matter spiraling inward at nearly the speed of light. These cosmic lighthouses can outshine entire galaxies containing hundreds of billions of stars, making them visible across most of the observable universe, despite being powered by regions smaller than our solar system. The discovery of 73 of these cosmic beacons arranged in a coherent pattern across 4 billion light-years challenged astronomers' understanding of large-scale structure formation. Like the Great Walls we explored earlier, the huge LQG appears to exceed the theoretical scale of homogeneity, the distance beyond which the universe should look essentially the same in all directions. What makes the huge LQG particularly intriguing is what it suggests about the early universe. Since we observe these quasars as they existed billions of years ago, when the cosmos was much younger and denser, the fact that such massive structure could exist so early in cosmic history implies that the processes organizing matter on large scales were remarkably efficient, perhaps more so than current theories predict. The quasars within the huge LQG are not randomly scattered, but show a distinct clustering pattern that suggests they formed within a large-scale structure of dark matter that existed when the universe was less than 3 billion years old. This raises fascinating questions about how quickly the cosmic web could organize itself in the early universe, and what this means for our understanding of structure formation. Some astronomers have questioned whether the huge LQG represents a genuine structure or simply a statistical fluctuation, a random clustering of quasars that happens to create the appearance of organization. However, detailed analysis suggests that the probability of such a large clustering occurring by chance is extraordinarily small, supporting the interpretation that this represents a real physical structure of unprecedented size. Moving from the largest associations of objects to mysterious absences, we encounter one of the most puzzling features in the cosmic microwave background radiation, the cold spot. This enigmatic region, roughly 1.8 billion light-years across, appears as an unusually cool area in the otherwise remarkably uniform afterglow of the Big Bang. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe in 2004 and has been confirmed by subsequent observations with the Planck Space Telescope. What makes this feature so mysterious is that it's far larger and cooler than the tiny temperature fluctuations that characterize most of the cosmic microwave background. One of the leading explanations for the cold spot involves a phenomenon called the integrated Sachs-Wolf effect, where photons from the cosmic microwave background lose energy as they climb out of gravitational wells created by large structures. If an enormous supervoid, a region of space with much lower matter density than average, lies between us and the cosmic microwave background, it could create exactly the kind of cold signature we observe. Observations have indeed revealed the presence of an enormous supervoid in the direction of the cold spot, nicknamed the Great Nothing, or the CMB cold spot void. This cosmic emptiness contains about 20% less matter than typical regions of space and spans roughly 1.8 billion light-years, making it one of the largest known voids in the universe. The existence of such a large void raises its own questions about cosmic evolution. Like the massive structures we've explored, supervoids of this size push against theoretical expectations about how empty regions of space should be distributed. The fact that we can observe both the largest concentrations of matter and the largest absences of matter suggests that the universe's structure formation processes are capable of creating more extreme conditions than simple models predict. Some researchers have proposed even more exotic explanations for the cold spot, including the possibility that it represents evidence of a collision between our universe and another universe in a multiverse scenario. While such explanations remain highly speculative, the cold spot serves as a reminder that the universe still holds mysteries that challenge our understanding of cosmic architecture. At the opposite extreme from these vast empty regions, we find individual galaxies that represent monuments to gravitational accumulation on truly staggering scales. The current record holder for the largest known galaxy is IC1101, a supergiant elliptical galaxy located about 1.04 billion light-years away in the constellation Virgo. EC1101 spans approximately 6 million light-years from edge to edge, roughly 60 times larger than our Milky Way, and more than twice the distance between our galaxy and Andromeda. This cosmic giant contains an estimated 100 trillion stars, making it about 500 times more massive than our home galaxy. To put this in perspective, IC1101 contains more stars than there are galaxies in the entire observable universe. This galactic monster did not achieve its enormous size through normal stellar formation processes, but rather through billions of years of galactic cannibalism, absorbing and merging with hundreds or perhaps thousands of smaller galaxies over cosmic time. Its smooth, featureless appearance tells the story of countless mergers that have erased any trace of spiral structure or ongoing star formation, leaving behind a vast collection of old red stars arranged in a nearly perfect elliptical distribution. IC1101 sits at the center of the Abell 2029 galaxy cluster, one of the most massive galaxy clusters known, where it continues to grow by consuming nearby galaxies. Observations show streams of stars being torn from smaller galaxies as they pass too close to this cosmic giant, adding their stellar populations to IC1101's already enormous mass. The existence of such massive galaxies provides insights into the efficiency of structure formation in dense environments. Galaxy clusters like Abell 2029 act as cosmic assembly lines, concentrating smaller galaxies in dense regions where mergers become inevitable. Over billions of years, these mergers build the supergiant elliptical galaxies that dominate the centers of the most massive clusters. Other notable galactic giants include NGC 262, which may be even larger than IC 1101, but is more difficult to measure precisely, and several other supergiant ellipticals that span millions of light years. These cosmic behemoths represent the endpoints of galactic evolution in the densest regions of the universe, showing us what happens when gravity has billions of years to concentrate matter into individual objects. Moving from individual galaxies to galaxy clusters, we encounter El Gordo, Spanish for the Fat One, officially known as ACTCLLJ 0102-4915. This cosmic heavyweight holds the record as the most massive galaxy cluster in the distant universe, containing the equivalent mass of 3 quadrillion suns and spanning several million light-years across. What makes El Gordo particularly remarkable is not just its enormous mass, but the fact that it exists at a time where the universe was only about 7 billion years old, roughly half its current age. The existence of such a massive, mature cluster so early in cosmic history challenges models of structure formation and suggests that the processes building the largest structures in the universe were more efficient than previously thought. El Gordo appears to be the result of a high-speed collision between 2 massive galaxy clusters, an event that generated temperatures of hundreds of millions of degrees and created shock waves that continue to reverberate through the system today. X-ray observations reveal the hot gas heated by this cosmic collision, while gravitational lensing measurements map the distribution of dark matter that makes up most of the cluster's mass. The cluster's extreme mass and early formation time provide important tests of cosmological models and our understanding of dark matter and dark energy. Clusters like El Gordo are so rare and massive that their existence provides sensitive probes of the fundamental parameters that govern cosmic evolution. Other massive galaxy clusters push the boundaries in different ways. The Coma cluster contains over 1,000 large galaxies in a relatively compact region, creating one of the densest galactic environments known. The Shapley supercluster contains dozens of galaxy clusters, concentrated in a region 650 million light-years across, representing one of the most massive concentrations of matter in the nearby universe. These extreme objects and phenomena reveal important truths about cosmic evolution and the processes that shape the universe's architecture. The huge LQG and other large quasar associations show us that significant structure existed very early in cosmic history, when the universe was young and the processes of galaxy and black hole formation were proceeding rapidly. The largest galaxies like IC 1101 demonstrate the power of gravitational accumulation over cosmic timescales, showing how billions of years of mergers and accretion can build individual objects that rival the size of entire galaxy groups. These galactic giants preserve the history of structure formation in dense environments, encoding information about merger rates and the efficiency of galactic cannibalism. The most massive galaxy clusters like El Gordo provide laboratories for studying extreme physics under conditions that cannot be replicated anywhere else in the universe. The temperatures, densities, and gravitational fields present in these systems allow astronomers to test theories of thermodynamics, plasma physics, and general relativity under the most extreme conditions nature can provide. Perhaps most importantly, these cosmic extremes serve as crucial tests of our cosmological models. The fact that structures as large as the huge LQG, as massive as El Gordo, and as empty as the cold spot can exist places strong constraints on the fundamental parameters that govern cosmic evolution. Each extreme object must be explicable within our understanding of dark matter, dark energy, and the initial conditions of the universe. The statistical properties of these extreme objects also provide insights into the nature of cosmic structure formation itself. The fact that we observe objects at the very limits of what theory predicts suggests that the universe operates close to the boundaries of what is physically possible, creating structures that push against the fundamental limits imposed by the age of the universe, the strength of gravitational forces, and the expansion of space itself. As we contemplate these cosmic extremes, we gain appreciation for the remarkable range of phenomena that the universe can create through the interplay of gravity, expansion, and time. For the largest associations of the most luminous objects to the most massive individual structures, from the emptiest voids to the densest concentrations of matter, the universe demonstrates an architectural ambition that spans the full range of physical possibility. These extreme objects remind us that we live in a cosmos capable of creating phenomena that stretch our understanding to its limits, where the processes of structure formation can build objects so large, so massive, and so extreme that they challenge our most fundamental assumptions about how the universe works. They represent the universe's greatest achievements in the art of cosmic architecture, monuments to the power of physical processes operating over billions of years across the vastest scales imaginable. As we near the end of our gentle journey through the universe's grandest structures, it feels natural to pause and reflect on what it means to be conscious beings living within this magnificent cosmic architecture, to consider how our newfound understanding of these vast scales changes our perspective on existence, meaning, and our extraordinary place within the web of creation itself. Here we are, you and I, sharing this quiet moment together while residing on a small rocky planet orbiting an ordinary star in the outer spiral arm of a galaxy containing hundreds of billions of other stars. Our Milky Way, vast as it seems from our human perspective, is itself just one galaxy among the roughly 80 members of our local group, a modest gravitational family that spans a few million light-years of space. This local group, in turn, sits within the Virgo supercluster, that collection of thousands of galaxies spread across 100 million light-years that we explored earlier in our journey. And even this supercluster is merely a small part of Laniakea, that immense heaven stretching 520 million light-years and containing roughly 100,000 galaxies, all connected by streams of matter, flowing like cosmic rivers through the darkness. But our address in the cosmos doesn't end there. Laniakea itself is woven into the cosmic web, that magnificent network of filaments and voids that organizes matter across billions of light-years, creating patterns so vast and beautiful that they preserve the quantum whispers of the universe's birth. We live within a cosmic architecture so immense that our entire observable universe might be just one small region of an even grander construction extending beyond our ability to perceive. It's humbling, isn't it, to realize that every structure we've explored tonight, from galaxy clusters spanning millions of light-years to great walls stretching across billions of light-years, represents the cosmic environment in which we find ourselves. We're not observers looking at the universe from the outside, but participants embedded within its very architecture. Yet there's something profoundly moving about this perspective. The atoms that make up our bodies were forged in the cores of stars that lived and died within this cosmic web billions of years ago. Those stellar furnaces created the heavy elements, the carbon, nitrogen, oxygen, and iron, that would eventually become part of planets and ultimately part of us. In a very real sense, we are made from the processed materials of cosmic structure formation itself. The calcium in our bones was created in stellar cores embedded within ancient galaxies that may have long since merged into larger structures. The iron in our blood was forged in the violent explosions of supernovae that enrich the cosmic web with heavy elements, spreading the seeds of complexity throughout the universe. We carry within ourselves the chemical legacy of cosmic evolution spanning billions of years and countless stellar generations. This means that our very existence is intimately connected to the largest structures in the universe. The gravitational collapse that built galaxy clusters and superclusters also influenced the formation of the molecular clouds where our Sun was born 4.6 billion years ago. The cosmic web's architecture determined the distribution of matter that eventually led to our solar system's formation in this particular spiral arm of our particular galaxy. When we look up at the night sky, we're seeing our cosmic neighborhood from the inside. Those faint smudges of light that reveal themselves as distant galaxies through telescopes are our neighbors in this vast cosmic city. The Andromeda Galaxy, that spiral of light approaching us at 250,000 miles per hour, is essentially the house next door on cosmic scales. In about 4.5 billion years, it will merge with our Milky Way, creating a new elliptical galaxy that astronomers have already nicknamed Milkomeda. This upcoming galactic merger reminds us that we live within dynamic, evolving structures. The cosmic web isn't a static framework, but a living architecture that continues to grow and change over billions of years. We're witnessing cosmic evolution in action, living during an epoch when galaxies still contain gas for forming new stars, when galaxy clusters are still growing through mergers, and when the largest structures are still taking shape. From our perspective within the cosmic web, we can observe the universe's history, written in the light of distant galaxies. When we look at galaxies billions of light years away, we see them as they existed when the universe was younger, revealing how cosmic structure has evolved over time. We're like archaeologists of space-time, using telescopes to excavate the universe's past and understand our place within its ongoing story. The cosmic web also provides the context for understanding life's rarity and preciousness. The conditions necessary for complex chemistry and biology require a delicate balance, enough heavy elements to build rocky planets and organic molecules, but not so much stellar activity that radiation sterilizes planetary surfaces. This Goldilocks zone for life appears to be most common in regions like our own cosmic neighborhood, nestled within the cosmic web, but not in its densest nodes. Galaxies within massive clusters, for example, tend to have their star-forming gas stripped away by interactions with a hot intracluster medium. Galaxies in cosmic voids, while peaceful, may lack sufficient heavy elements to build Earth-like planets. Our location within a modest galaxy group, connected to but not overwhelmed by the cosmic web's dense structures, may represent an optimal environment for the emergence of complexity and consciousness. This perspective transforms how we think about our significance in the cosmos. Rather than making us feel small and insignificant, understanding our place within cosmic architecture reveals us to be participants in the universe's grandest achievement, the emergence of matter complex enough to contemplate itself. We are the cosmic web become conscious, structure formed from the same processes that built galaxies and clusters, but organized in patterns intricate enough to experience wonder, create beauty, and seek understanding. The fact that conscious beings like ourselves can arise within cosmic structure suggests something profound about the universe's nature. The same gravitational forces that assembled galaxy clusters over billions of years also concentrated matter on smaller scales, creating the conditions where stars could form, planets could condense, and chemistry could become complex enough to support life and consciousness. We represent a remarkable convergence of cosmic processes: stellar nucleosynthesis creating heavy elements, planetary formation concentrating those elements, and billions of years of evolution organizing matter into patterns capable of thought, feeling, and cosmic contemplation. In us, the universe has developed the ability to observe and understand itself, to appreciate beauty across scales from quantum to cosmic, and to feel awe at the magnificent architecture of which we form a part. Our journey through the largest structures tonight has revealed that we live within a universe of extraordinary organization and beauty. From the cosmic web's delicate filaments to the massive galaxy clusters at its nodes, from the vast emptiness of cosmic voids to the dense concentrations of supermassive black holes, we've seen that the cosmos displays patterns and structures of breathtaking complexity and elegance. And yet, for all the vastness we've contemplated, perhaps the most remarkable structure in the universe is the one experiencing this very moment of wonder: the intricate pattern of neurons and consciousness that allows you to comprehend these cosmic scales and feel moved by their beauty. In a universe that has taken 13.8 billion years to create structures spanning billions of light years, the emergence of awareness capable of appreciating that architecture represents an achievement of staggering improbability and profound significance. As you drift off to sleep tonight, carried by the same gravitational forces that organize galaxies into clusters and clusters into superclusters, remember that you are not separate from the cosmic web we've explored together. You are part of it, a local concentration of matter and energy that has achieved the remarkable property of consciousness, embedded within structures so vast they connect you to every corner of the observable universe. The cosmic web cradles us all from the smallest microbe to the most complex human civilization within its gentle embrace. We are children of the stars and citizens of the cosmos, temporary but precious organizations of matter that have inherited the chemical legacy of billions of years of cosmic evolution. In contemplating the universe's largest structures, we discover not our insignificance, but our profound connection to everything that exists across all scales of space and time. Sweet dreams within this cosmic embrace, knowing that you carry within yourself the story of the universe's grandest architectural achievements, and that in your capacity for wonder and understanding, you represent the cosmos discovering its own magnificent nature. This is the sleepy astronomer, wishing you the most peaceful rest among the largest, most magnificent structures ever discovered, and reminding you that you too are part of this cosmic masterpiece, forever woven into the infinite architecture of space and time.